1, go!
Hi, I'm Tektronix,
And I'm Lucas Portelli.
and we're going to show you what we did with the Tektronix oscilloscope. Our project is to measure time-varying magnetic fields using an induction coil that we built. And
A triaxial coil.
Triaxial, so we can measure all three directions at the same time. And a Tektronix oscilloscope. And the signals that we pick up with this guy are really tiny, so we're using a 1000x amplifier. And
They're in the order of microvolts.
exactly. So if we look at the channel, what we're picking up here, we can swap between our different directions and see the signal going in every way. The best part about this, though, is if we switch to our FFT, it then gives us a full analysis of the spectrum, showing right here a peak at 60 Hertz. Because we are in America, we have fields from the wall that we can pick up. And the rest of the spectrum is mostly noise, but there are some multiples of the 60 Hertz that you can see as well.
Now, what happens if you shield that with a mu metal shield that we have right here?
That's a very good question, Lucas. If we put this inside of the shield,
The other way.
from the side that it fits, and we wait for the refresh, and there it is. The spectrum has mostly flattened out. The 60 Hertz has dropped significantly, which means we're actually measuring the fields. A probe works, our oscilloscope works, and the mu metal works. Now, the next step of this project would be to see what a reading on the oscilloscope, the FFT, corresponds to a reading of a real field. For that, we used this square Helmholtz coil
We built this square Helmholtz coil.
and carefully leveled everything to make sure the parameters are exact. We know what field we're making. And then you just put the probe directly in the center, which my cable's not long enough right now, and you turn on a field, or you turn on a current, create a field. You know what field you're creating. You can measure it on the oscilloscope and
You can
calibrate
calibrate
it that way. So how well did that work? Well, we have over here an older oscilloscope that has a CRT screen. As we know, these are famous for putting off a lot of noise. Let's see how much it does. If I just put the probe directly in front of the screen, I'll hold it right there, and you can take a look at the screen here. I have to change the scale on this channel. And okay, there you go. We're at a 1-volt scale. I'm going to change my amplification down to 100x because there's so much noise here. We can bring that up so it's visible. And then go back to the FFT. And that's picking up order of maybe 100 or 1,000 times more than what's around in the room without the CRT screen.
And we can change between the channels. So if we see what the field is in another direction, that's it. And even in another direction, that's it. So it's pretty big.
And as far as sensitivity, we found that we're able to detect a field as small as 1 microtesla oscillating at 1 Hertz. That's 1/50th the magnitude of the Earth's static field on average. And the nice thing about this is, since it's an induction probe, we scale linearly with frequency for sensitivity. So at 100 Hertz we could detect 0.01 microtesla, which is really quite fantastic.
And it beats the probe we had to buy for $500, which is not inductive, and it's a Hall effect probe. This is $500. We built ours for near to nothing.
20 bucks and a Tektronix oscilloscope. Thank you for watching, and have a good day.